Any questions or comments from last time? Let's keep going. We wanted to study the collapse of a spherical dust-like star. Okay. Since last time, I realized that Landau-Lifshitz also has a discussion of this thing, and sort of as usual, they do it in a slightly simpler way than the original papers. So let's follow their notation. Okay, so the metric we're interested in is ds squared is equal to the tau squared, this hasn't changed, minus e to the power lambda, I think we called it w last time, the r squared, plus r squared the omega 2 squared. I think last time we called this e to the power omega bar. We call this e to the power w. I've just changed notation. We have two free functions, this guy and this guy. It's a bit more convenient to keep this exponential.
Yeah, capital R.
This is not the same. R is equal to some unknown function of r and tau. That was what was our e to the power w bar. You just change notation to bring this down. Okay. Also emphasizes the physical meaning of this this little r. Okay. Lambda is whatever it is. Okay.
And lambda is also a function of capital R and tau.
Sorry. Okay. So as we discussed before, we're in these co-moving coordinate. Tau is a proper time. Capital R is some arbitrary label for shells of dust, and little r is the actual physical radius of the shell of dust. What does physical radius mean? It means the radius such that the area, the proper area of that sphere would be 4 pi little r squared. Yeah, as you can see from here. Okay, excellent. So now we want to set up Einstein's equations. So it's, you know, the usual job. We first question, how many different equations are we're going to have? So clearly we'll have an equation which is like TRR, you know, the equation which on the right hand side has stress tensor RR. We'll have an equation which on the right hand side is the stress tensor, let's say RT, R tau. We'll have an equation which on the right hand side has the stress tensor tau tau. And then we'll have the equation which has T alpha beta, where these are coordinates on the sphere. But we only get one equation from that whole thing, because everything on the right hand side will be like delta alpha beta. G, it will be proportional to G alpha beta, but upper lowers of delta alpha beta. This is, you guys are now used to all this, right? So we'll have 4 different equations. I'm going to write them down. Okay? We won't try to work them out again. We'll just trust Landau-Lifshitz and write them down. Okay. What I did was work them out enough to know which was what equation. That they don't say. So the TRR equation is e to the minus e to the power minus lambda r prime square plus 2r r double dot plus r dot squared plus 1 is equal to 0. So this is just a label for the equation, okay? Why was it equal to 0? It was equal to 0 because you remember that the only stress tensor we had on the right hand side was TT. So this is the only equation that will have a non-zero right hand side will be this.
So it wouldn't probably matter in the other equations because it's equals 0 anyway. But in the TT equation, and Landau-Lifshitz have this opposite metric convention as to what we are using, and he has a plus minus signature.
Will this matter? You're right that he, but you know,
I mean, it will probably differ by the overall sign, that equation only.
Will the equation, well, the overall sign, of course.
Yeah,
Yeah.
zero equations, it wouldn't matter.
Right. You're asking whether I will get, whether my as long as we keep track of the fact that the stress tensor is a positive quantity, for instance, I think we'll just be okay. Right? Because Landau-Lifshitz, as you're right, will have a minus of this metric.
Yeah.
But in the end, we will want the physical quantity is the coefficient of this, after the minus sign has been stripped away, and that's what we're computing the equations for. Okay, so I'm not writing Landau-Lifshitz metric like this. Yeah, so I think my equations will be okay when I write them down. Okay, the equation that was tau r was the simplest of the equations. It was 2r dot prime minus lambda dot r prime is equal to 0.
And dot is with respect to tau and prime is with respect to r, right?
Exactly. So dot means derivative with respect to tau, and prime means derivative with respect to r. Okay. Then let's write down the tau equation. This is a complicated looking equation. It's minus e to the power minus lambda by r squared into 2r r double prime plus r prime squared minus r prime lambda prime plus 1 by r squared into r dot lambda dot plus r dot squared plus 1 is equal to 8 pi k. K is Newton's constant.
K is G.
8 by g epsilon, where epsilon is the proper energy density of the dust. We'd written down last time what our stress tensor was. Do you remember? You want me to write that down again? So the stress tensor T was equal to epsilon u mu, T mu mu. Mu was equal to epsilon u mu u nu. Okay, where epsilon was our epsilon, and u was dt normalized. Oh yeah, in this case it's just dt. Okay, so T tau tau was equal to epsilon. Okay, excellent. And so there was one last equation. Let's write that down. The equation that came from the sphere was the following, also quite complicated looking equation. Minus e to the power minus lambda by r 2 r double prime minus lambda r prime lambda prime plus r dot lambda dot by r plus lambda double dot plus lambda dot prime prime dot squared by 2 plus 2r double dot by r is equal to 0. This one?
No, yeah, this one and also.
This one is r, yes.
R and that's r dot lambda dot over r.
R dot lambda dot over r, correct. Okay, so these are our equations, and now we want to go about them and solve these equations. Okay, so in order to solve these equations, what do we do? Well, let's take this equation here. This equation, let's read as an equation that as a linear equation that we can use to solve for lambda. You see, it's very simple. We solve it by integration. So, how do we integrate this? So, lambda dot is equal to 2r prime dot divided by r prime. Okay? But this is same as 2 of log r prime dot and therefore lambda is equal to 2 log r prime plus some unknown function of r. That, you know, this is really a differential equation in time, so it's up to a constant. So that constant could be any function of little r. Okay? Therefore, this equation is e to the power, and I think Landau-Lifshitz called this 1 plus. I think they write it as 1 plus f. I'll check that in a minute. I mean, they're free to do it. Constant. 1 is as good a constant as f. So now we exponentiate this. Oh, maybe even this is some function of r. We'll okay. I'll just call it alpha of r and then fix it in terms of Landau-Lifshitz later. So e to the power lambda is equal to r prime squared times some function of r.
Yes.
And Landau-Lifshitz called that whole thing for their own reasons 1 over f of r. Excellent. Okay. So we've done well. Out of the 2 unknown functions in the metric, we've solved for one of them, namely this lambda. We've solved for one of them. Already in terms of the other one, and we've got one free function of r in the process. Okay, great. Now, the next thing they do is to substitute this into the RR equation. The RR equation has minimal reference to lambda. Okay, so it gets least contaminated by doing substitution, so let's do that. So we've got this equation is now minus 1 plus f of r, because the r prime squared and that 1 by r prime squared cancel. Okay, plus 2 r double dot plus r dot square plus 1 is equal to 0.
The 1 cancels.
The 1 cancels. That's probably why they write 1 plus f of r. Okay, and so our equation becomes minus f of r plus, let's write it as r dot squared plus 2r double dot plus minus f of r. ddt of what? No, be a bit careful. R dot square will not have an r.
And we'll multiply by something.
However, the intuition is the right intuition. You see, because suppose when you think about this for a minute, the first thing you notice is that this is homogeneous in R's. So that's the key. Can I? Maybe not. What should I clear? I'll clear this. Okay, you'll remember what. This part, fine. I'll clear up to here. Okay. Now you see, So suppose we take the structure r times r dot to the power m. Suppose I take that structure and I differentiate this dot. What will I get? I will get, the first term is when I differentiate this, I will get r dot to the power m plus 1. And the second term I will get will be plus m times r double dot times r dot to the power m minus 1. So you see this, which is equal to r dot to the power m minus 1 into r dot squared plus m r double dot. Okay. The important thing is that this had the number 2. So we will choose m equals 2. Okay.
M equals 1. Oh no, m equals 2. Sorry.
Hang on, yeah. So we'll write this as, so this whole thing is equal to r dot squared dot, but we don't get quite this because there was this r, so divided by r dot. Minus f of r is equal to 0. Now we take the r dot to the other side.
And that.
Huh?
T is not.
What?
T can be.
Exactly. And f of r is a function of r, but it's not a function of t. So we can just integrate. And therefore we find r dot squared minus f of r times r
Is a function of tau.
is function of r.
Tau.
R.
Oh, R. Yeah.
Okay. Is some other function of r. It's a constant of integration, but this is an integration with respect to tau, therefore it's a function of r. Now we'll have to see what Landau-Lifshitz calls this function. He calls it capital F. This is some capital F of r. And therefore we can write this as this divided by r. All good? Excellent. Now, how are we going to solve this equation? Any ideas? Exactly. Exactly. You see, all the rest of you were fooled by this capital R. Capital R is a fake. It's a constant. So imagine this is some particular value of capital R. We're working at some particular, this is a constant, this is another constant. So this is the kinetic energy. Bring it on this side, it's the potential energy. Take that on that side, it's the total energy. So now we're all experts. Okay? So what?
1 by R equals something 1 over L into 1 plus epsilon.
Something like that. Let's. Yeah. So this is r dot. So we'll take everything to that side first. Is equal to f of r by r minus plus f of r square root plus minus. And therefore r dot is equal to plus minus, and therefore now we do the usual thing. Just remember in all of this, the only confusing thing about all of this is this capital R. Remember that it, as far as we're concerned, is a constant. Okay, and so this is dr divided by square root of f of r divided by r plus f of r is equal to d tau.
This line is more important.
Right. Okay. I'll keep these equations on the board for a bit. I'm clearing this part. Okay. And just to show that we can, that we can, just to show that we're going to solve it in general. I will later focus on one special case where the solution is very simple. But let me just first do it in general. Okay, so all we have to do is to do this integral, dr divided by. So the kind of integral that we want to do is dx divided by integral of ax plus b. Okay. Now, what this integral is will depend on whether the signs of various things. And what have we assumed for the signs? Just a moment. I think we should treat capital F always as positive, but little f, we should treat capital F always as positive, because otherwise near our
Zero.
exactly. Remember r, little r is the physical radius, which will go all the way down to 0. Okay, so unless our capital F was positive, we would have trouble here when r was 0. So let's assume that this capital F function, whatever it is, was positive. This guy though could be either positive, negative, or 0. Okay, we'll have to work out each in turn.
No, I mean, can't we just obtain a general solution, making no assumptions about the sign, and when the need arises, make some analytic continuation for some solution?
We could do that. We will be particularly interested though in the case this is equal to 0. So it will be easier to okay. Okay, then all this of course is quite trivial, but let me quickly just go through this. Okay, first let me assume everything is positive. When this is 0, this is trivial, right? Let's do that first. Okay, so f of r is equal to 0. Then this integral is dr divided by f of r square root times r, and therefore is equal to 3 by 2, so 2 by 3 r to the power 3 by 2 divided by square root of f1. Okay, so this would be equal to tau. This would be equal to tau, but now there's also another integration constant in this thing. We'll call this new integration constant
Tau minus tau.
yes, tau naught, but that's a function of r. So tau minus tau naught, which is a function of r, and now we have to be careful about the sign. We had this with the plus minus. Okay, let's first study this case, and then I'll quickly tell you about this. What we're interested in is looking at this shell of dust collapsing. So as tau increases, r should decrease. Therefore, we got the sign wrong. Okay, so we'll write this as tau naught of r minus tau. The other one's also, a solution.
It is a solution.
Yes,
Yeah,
this is,
it's
it's looking a little. It's but in fact, with that solution, you would hit a fixed radius and then come back. Okay, but we're not interested in that part of it, that part of the motion. So we'll just focus on this. Okay, so in the case little f is equal to 0, we've finished solving. In the case little f is equal to 0, we finished solving. What is our solution? Our solution is tau naught of r minus tau maybe we'll want to view it as r as a function of this. So we will get r is equal to tau naught of r minus tau to the power 2 by 3, correct? Now I take this to the power 2 by 3, so that's f to the power 1 by 3 of r, and then we've got an unpleasant number. 3 by 2 to the power 2 by 3. Yeah, this agrees with what Landau equations are. Okay, so in this particular case, this choice f is equal to 0. What do we have? Well, this thing here is physical. It tells you about the motion. Remember, what we were doing was sitting on a particular shell of dust. Capital R labels a particular shell of dust. So if we keep capital R fixed, then the tau dependence gives us the motion of the physical radius of that shell of dust. Okay? So it gives us the motion of the physical radius of that shell of dust. So now you see that this tau naught of R is a very physical quantity. It is the quantity that tells you at what time does the shell labeled by a label capital R hit the center. Right? Okay? And so that's what this tau naught of R is. Now we've got this f of R. This f of R is actually much less physical. Well, some combinations less physical for the following reason. You see, so far in here there was a redundancy of our parameterization. Can anyone tell me what it is? What change of variables can I make here that will keep this metric of the same form? And what does physically mean? Scaling R, shifting lambda. Well, you don't have to have shift, because since I haven't told you anything about what lambda is, you can scale R. So that also tells you that scaling is too limited. R goes to any function of R. We'll change lambda by some function of R, but who cares? I didn't know what lambda was anyway. Okay? Physically, what does it mean? R was used as a parameter to label shells of dust, but I told you nothing about what that parameter was. So if you use one parameterization, I can use any function of your parameterization as my parameterization. Okay? So clearly, we had to have that symmetry. So everything here, in everything we've done here, we've not fixed that parameterization symmetry. So in everything we did here, we had 3 functions of R. There was this tau of R, there was capital F of R, and there was little f of R, which I just in this particular case happened to set to 0. But in the most general case, the case where little f is, let's say, positive, and you work out this integral, everything will depend on 3 functions of R. But there's one parameterization ambiguity that you can remove by some physical requirement that you like. Okay? So the actual solutions will be parameterized by 2 functions of R. Okay? And the 2 functions of R, well, one of them, we've understood what one of them is. It's basically, it is the position and the velocity of each shell of dust. See, suppose I wanted to give you, I wanted to parameterize, just think in classical, not in relativity, just got some dust moving around in some spherically symmetric way, and I wanted to characterize the most general dust configuration. What I would need to do is to characterize its density at some time and its velocity at some time. These are two functions of R. And then any evolution equation will tell you how everything moves in the future. Okay? So that's what you should expect, that your data is parameterized by two functions of R, which are essentially the density of the dust cloud and the velocity of the dust cloud. We're seeing solutions in terms of three functions of R because we've got one redundancy. So effectively we've got a two-parameter set of solutions. These are initial conditions, exactly. So initial conditions are just up to us, and because we've got this dust lying around, there's plenty of initial conditions. Note that if we had gravity without matter with spherical symmetry, since there are no gravitational waves that are spherically symmetric. Actually, you guys don't even know that, right? Anyway, we need to give you another assignment on gravity waves, a little more.
Because of the quadruple nature?
Because gravity is spin 2 essentially, that's right. Another way of saying it is that there are no, the set of spin 2 spherical harmonics of angular momentum 2 start at L equals 2.
L equals 2.
Right. Just like vector spherical harmonics start at L equals 1. This is something you probably know. It's more general. Spin S spherical harmonics start at L equals S. That's the...
There is no spherical symmetry.
There's no spherical symmetry.
There's no spherical symmetry.
That's right. That's right. This is by the way the underlying reason why it was so easy for us to find the Schwarzschild solution. In pure gravity, there was no play once we assumed spherical symmetry. And this is the underlying reason behind what is sometimes called Birkhoff's theorem, namely that in the absence of matter, any spherically symmetric solution of general relativity outside, suppose there's only some matter in some certain region, and you look at any any spherically symmetric solution of general relativity outside that region, it is necessarily of the Schwarzschild. Whether it's time dependent, independent thing, that's the key thing. We haven't quite proved this because we, right from the beginning, searched for, when we looked for the Schwarzschild solution, we searched for time independent solutions. So of course we weren't going to find gravity. But even if we hadn't done that, we would have got the same solution. The equations would have been strong enough to tell us that with the assumption of spherical symmetry, time independence was automatic. Okay? We didn't go through that exercise, but it would have been. And this is the heart of this thing called Birkhoff's theorem, which tells you that if you've got a spherically symmetric situation, whether it's time independent, dependent, doesn't matter what, as long as there's no, outside the region where there's matter, the solution is Schwarzschild. So essentially the statement that there are no gravity waves that preserve spherical symmetry. Okay, so this is sort of important because it greatly simplifies these dust solutions. Why is that? It greatly simplifies the dust solutions because had we not been spherically symmetric, or had spherical symmetric gravity waves been around, then what would have happened is that the dust moving around here would have led to radiation, which would have impacted the motion of the dust there. Okay? And that is a whole different level of complexity in the solution. Okay? But this is a very simple problem because basically nothing is happening except a simple spherically symmetric warping of space-time. No time dependent. Okay, that really helps simplify the solution. This is why this problem is so tractable basically. This should also warn you, by the way, that maybe new interesting phenomena happen when you go away from spherical. As usual in physics, there's a playoff between solvability and interest. There's more or less a theorem which says that no problem that has an exact solution is interesting. Okay. Okay, but let's keep going. So let's postpone this for the end. Okay, let's see, immediate, actually why don't you guys work this? Wait. Do these in, okay, so as an exercise. This is just to show that it's very trivial to solve the most general dust collapsing situation. What we're going to do in the rest of this, the next 5 minutes, is to look a little bit at, some simple examples of these solutions. Okay. Now the last thing I want to do with this solution here is to, okay, so this is the solution, and we had equation number 1 somewhere. So we found R, and we had found e to the power lambda. Can somebody help me? R prime square or 1 plus little f, but in this case little f is 0, so e to the power lambda was R prime square. Okay, so let's write down a metric already at this state. ds squared is equal to minus d tau square. ds squared is equal to minus d tau squared plus r prime. Yeah, so let's evaluate r prime. Okay, let's actually further specialize. I'll do this in a minute. Now I'm going to make this even more special. Okay, let me go to the case where little tau of r is a constant. What does this mean physically?
That all dust shells collapse at the same moment.
Oof, what a singularity, right? Yeah. So all the shells at the same value of tau, this tau coordinate, at the same proper time on the shells are going to go whoop, and go to the origin together. Okay, so I can make that choice.
Okay.
Who can stop me? If it's a if it's a solution, it's a solution, right? So tau naught of r is equal to tau naught. So more seriously, what could stop you from making this choice is the realization that the solution is somehow singular. Okay, well, that's what you're going to investigate in an assignment. Right. Okay, so
the central part of the dust is not moving at all in this code.
the central part.
Every cell will collapse.
You're right. You're right. You're right. Yeah. Yeah. So basically, it's somehow be tuned to the velocities, so that they're all going to arrive at the same time, and that means, in particular, that the central part is moving very slow. As you go slower, it's moving slower and slower. Okay. At this point, clearly, you're going to have a singularity in your solution. It's obvious because the clearly the density of the dust is going to go to infinity. We'll check that. Okay. Now,
So when you say density, what does density even mean when you have a singularity in the space-time itself?
yeah, it's a good question, but as we approach this point, the density will blow up.
No, I mean, what's the density measure? I mean,
Epsilon.
What are you dividing it with? What's the volume measure?
It's this proper density, this epsilon that we were interested in.
Oh, I see. Epsilon itself.
Yes, epsilon, the coefficient of u mu in the stress tensor.
Yeah.
Using this same parameter. Yes. Oh, now you might ask, what if I do a reparametrization of R? But there's one function that doesn't change under such a reparametrization, namely constant. Okay, so in every choice of parametrization, it will be a constant. You see, physically, what we've got is that all dust shells come and hit at the same point, and that is a parameterization independence. Okay. Excellent. So, we made this lovely choice, and so now r prime is equal to, I made this choice before doing r prime, so I didn't. Wow.
Two-thirds.
Oh, so it was 1/3?
No, no. I mean, you have already fixed it to a constant. So why differentiating this?
Oh yeah, no, yeah, absolutely. Thank you. Oh no. 1 by 3. You're right. By f by 3, f prime of r, and then 3 by 2 to the power 2 by 3. Okay, and so our metric is ds squared is equal to minus d tau square plus squaring this. Right? Okay, these numbers. Okay, squaring at least gets rid of this.
No.
Oh, 4 by 3. Sorry, 4 by 3. Sorry. So that's 1 by 3 squared, 3 by 2 to the power 4 by 3. Okay, so you can combine this in some way. Tau naught minus tau to the power 4 by 3. F prime r, the whole thing, squared d r square.
And there was one f to the 4 thirds in the
F to the 4 thirds. Thank you. By f to the 4 by 3. Okay. Great. Plus r square. Plus this tau naught minus tau to 4 by 3. F to the power 2 by 3. 3 by 2 to the power 4 by 3 d omega square. Okay, before making any further choices, which we're going to make in a minute, there are two things we should do. Firstly, we've got two Einstein equations. Okay, we've got two Einstein equations we haven't used at all.
Yeah.
We've used this and we've used this, but these two guys have been basically unused. Okay, now I'm going to plug in our solution into this equation and use that to find how epsilon is as a function of r and tau. And it will turn out that this equation is just identically obeyed by our solution. Okay, so this equation is just basically fake. Of course, you've seen many examples of how these things work. Right?
So it's because we have only 3 parameters in our solution and it's parameter, basically parameterized by 2 of them.
Yes.
Which are fixed by the first 2 equations, and the third equation determines the energy density. Is that so?
That's right. And the fourth equation is basically, you see, the third equation is an independent equation because there's the conservation of the stress tensor. Because there's the equation of motion of the dust itself. That was there. The fourth equation was clearly not independent at all because there were 2 variables in our metric. There should have been 2 equations. Okay, there's a third because there's also the matter equation of motion. Okay, fourth cannot have been independent. And this is the usual story, right? It's the Bianchi identity that guarantees that these equations were not identical, were not actually independent. Okay, but let's quickly do the algebra to see that we can to see what this equation is telling us. So I'm rubbing out these 2 equations. Okay, so let's quickly do the algebra. So here we have minus e to the power minus lambda. Yeah. Okay. So here we have this r prime squared, the other way. Let me first write it in terms of r prime, and then we'll simplify. Okay. So what we'll write, what we'll do is minus. This is 1 by r prime squared, right? 1 by r squared r prime squared into 2 r double prime plus r prime squared minus r prime lambda prime. Now lambda prime was lambda was r e to the power.
2 log r prime.
Was 2 log r prime. Excellent. And so we will get 2 log r prime. So r double prime divided by r prime.
Yeah, and even r prime square cancels with r prime square
Downstairs, yes. Okay, but double prime. Yeah, so this and this cancel. So this first term here was just minus 1 by r square. Okay. Now let's get the second term. It's plus, but there's a plus 1 by r square plus 1. So the minus 1 by r square cancels that. Okay. So what remains is 1 by r square r dot lambda dot plus r dot square is equal to 8 pi g epsilon. That's what remains. Okay. Now we need to put in. Again, we'll put in what this guy was. So this guy was r dot prime by r prime with a 2. Okay, and now we need to use r dot. I maybe should not have. Probably even without using the, possibly even without, we just use the. There was that one very simple equation. Can somebody help me with that?
The second Einstein equation.
Yes.
2r prime dot equal to, but then again it's in terms of lambda dot. It is equal to lambda dot r prime dot. R prime.
Just a minute. Okay, well let's just plug it. There's probably some clever thing to do. Let's just plug it. Maybe just plugging this. Yeah, I suppose just plugging this. Wait, I'm sorry. One more request. At some point we had that equation that we solved for r.
R.
That was an equation which had r. No, but there's no prime. There was no prime.
Yeah, r prime square can be expressed purely in terms of r. R prime square is simply capital F over small r.
R prime squared is capital F over small r. Okay. R dot square.
Sorry, R dot square equals to capital F by smaller, right?
Okay, yeah, but this complicated guy is not going away. So let me just substitute and see what we get. Okay, so now we substitute. So R is equal to this. So what do we get? R dot prime by R prime. Okay. Now let's see.
R dot prime is prime of R dot square over 2.
Good, good. But see, notice that the R dot on R dot prime acts only out here.
Yeah.
And this was a constant. So the R prime part
only on that one.
exactly. So this R dot prime divided by R prime is derivative of this divided by 8. Okay, and therefore I'm clearing. So this is 1 by R squared 2R R dot into 2 by 3 1 by tau naught minus tau with a minus sign. Okay, great. And then we have 2R R dot by R squared. So this R and R squared of course goes. So this was there was this. So this is R dot divided by R. Same thing. And therefore this just gets squared. And so this becomes plus 2 the whole thing square. Okay, that was this term. But then we also had plus R dot squared divided by R squared. That's exactly the same thing. The only difference was this factor of 2 was there. So it becomes a factor of 3. So we get 3 into this. Okay, so this is 8 pi g epsilon is equal to this quantity. Okay, so we made various very special choices. We made various very special choices. And now we see what those special choices corresponded to. You see, at any given value of tau, the density is constant. So what we looked at was a uniform, homogeneous ball of dust with velocities tuned so that all shells will make it to the center at the same time. And notice that as tau goes to tau naught, the proper density of the dust is blowing up. So we shouldn't expect the solution to be valid beyond tau is equal to tau naught. Something clearly crazy is going to happen at tau equals tau naught. Okay? Fine. So now we've got our solution. So our solution, look here, has this tau.
Zero function of R is the initial condition, not the choice of that freedom.
No, actually, yes, it was an initial condition because that was physical time. Actually, the choice of this freedom is essentially the f of r, at least in our case, because you see that this f of r can be changed by changing r. You can move to f as your variable, for instance. here because f prime dr is df. Exactly. So if we move to f as our variable, this whole thing becomes very simple because everything's now just in terms of that variable. This has an f to the so if you let's do that. There's no reason not to. Okay. So this metric is ds squared is equal to minus d tau square plus shall we get this power of it's not worth it. Okay. Plus this number. Tau naught minus tau to the power 4 by 3 over f to the 4 by 3 df square plus tau naught minus tau to the power 4 by 3 f to the power 2 by 3 d omega square. That's f squared. Very nice. F squared by f to the power 4. Okay, so let's write this even more simply. That's ds squared is equal to minus d tau square plus tau naught minus tau to the power 4 by 3 divided by f to the power 4 by 3.
However, the factors over there, the number is 1 over 9 additional factor in over there. And this 1 over 3 squared which was there, which is there, is not here, but we can fix it by scaling.
It's fine. Just remind me, why did we, where was this additional 1 over 3 squared from?
Because we had done r prime.
R prime and that, I see. Yeah, yes, we were probably right. So let's just keep that. Df squared by 9, that's what you're saying, plus d omega 2 square.
Df square.
Into f square. No, it can't be. I mean, if you do scaling, that will change the fact of this. Yeah, it's okay. It's okay. Just keep this as it is. Okay. So what are we seeing? We're seeing that as proper time progresses, see, f was a function of capital R. So f is as good a parameter of the shell as capital R was. Okay. So what we're seeing here is that fixing on a particular shell, A, the size of the sphere becomes smaller and smaller and smaller. Okay. And B, that radial distances between spheres become smaller and smaller and smaller. Okay. Okay. So we've got a very pictorial. It's a very simple pictorial metric that we can get a good picture of. Okay. We've already taken small f is equal to 0. So that was a special case.
Doesn't that fix the scaling?
No, actually, that was a choice of. That was a particular choice of physics. You see, that small f equal to 0 was sort of crucial for what? Let me get that straight.
So maybe this is the
It was.
f r is equal to 0 and tau r is equal to tau naught are the two initial conditions.
What is the fix? Say again.
This f,
Uh-huh.
defining the f as the radial coordinate.
No, well, yeah.
Is that the
I mean, we just moved coordinates to f.
And there's no new physics involved in this.
In this step. Uh, it was, okay. I think that those, yeah, let me think just a minute. You're asking physically what did we do by setting little f is equal to 0. I think that we narrowed in on a one parameter set of solutions rather than two parameter. But let me try to, I don't think that was just coordinate. Yeah, I don't think that was just coordinate. To make that really clear, we should solve the full problem, then fix the additional invariance completely and see what we get. But I'll tell you what I think is going on. Just a minute. I mean, I think the question is, if we can ask, if we set little f equals 0, see, this is, you see, what did we have? We had e to the power lambda is equal to r prime squared over 1 plus f 1 plus f. So you are right that if I change coordinates, that changes little f, because that just changes r prime squared, and that is this this business. Yeah? So you could ask me the question, what was special about f equals 0, since I could change it by well, certainly f is equal to 0 and tau 0 of r was equal to constant. Together were quite special. I don't have a complete answer to your question. To get a complete answer, we would actually, one way of getting a complete answer would be to solve the whole problem and then set the ambiguity. But we clearly see that even at this stage, there is a coordinate freedom left. So it couldn't be that setting that has completely killed the coordinate freedom. Okay, so I should have a better answer to your question. F equals, I think it is an initial condition. I think that at least the combined thing, f is equal to 0 and tau 0 of r is equal to 0 is completely physical.
Actually, just set the time at which this is.
Yes.
So, like, I mean, what if, like, time can be set both the position and the velocity. So, we can just set the position of the shell at the first one, the f r equal to 0.
F of r equals, I think that is what is going on, more or less. You see, because as we see from here, we've got an essentially unique solution.
Yeah. F is not a key function.
F is a coordinate now.
It's just a coordinate.
Yes. So we've got a solution which is labeled by just one number. Okay. So effectively what we have done is set both the position and the velocity of our dust clouds up to one number. Okay. So the full sequence of steps is doing this, and how to break it up maybe is not even completely invariant. Okay, but in the end we've got one solution which is doing this. We should probably explore the more general.
And we got lucky because f equals 0 and tau naught equals constant constitute a consistent set of initial conditions.
Well, everything was consistent.
No, I mean,
It was just free
no,
from.
I mean, not necessarily two, because, I mean, they could be related in some way, but in this case at least, they turned out to be consistent initial conditions.
Well, the consistency is guaranteed. But the question, you may be asking whether they're physical or could be changed by coordinate transformations.
Yeah.
Maybe that's the question you're
That
asking.
could be.
Yeah, that maybe I would have to think about that. Okay, but anything was consistent. These are all solutions.
Yeah.
There's another question of which of them are coordinate equivalent and so on. Okay. Now there was one last thing I wanted to say before we try to make a few qualitative remarks and move on. Okay. What was that last thing? The last thing was, let us remember what our R was. So, suppose we start looking at this problem at R is equal to tau equals 0 for a moment. Imagine that our initial conditions were set at tau is equal to 0. What does tau give us? What does tau give us? It gives us yeah, no, this is what I was going to say. Just forget. Well, I suppose what we want to say is that we had this epsilon is equal to constant. We had this epsilon is equal to constant, but we should cut this solution off somewhere. You see, we have the homogeneous dust cloud. But we don't want to study a homogeneous dust cloud that extends out to infinity. Okay? So the original coordinates, we should cut this solution off at some r. Okay? Or in these coordinates, we should cut the solution off at some s. Okay? So we've got these dust particles that are labeled by f, these dust shells that are labeled by f, and they go up to a certain maximum f. F goes to 0, and then up to a certain maximum f. So that's exactly. So f is less than f naught. We should always keep this in mind. There's some there is some maximum radius. Okay. What the value of that radius is depends, of course, on time. But at any finite time, there is a maximum radius. At t equals minus infinity, there's no maximum radius. Okay, it's very dilute dust shell, very dilute because of, where's the epsilon formula gone? Very dilute because of this. Okay, so t is equals minus infinity, very dilute dust shell that is extending all over space. It's coming in, coming in, coming in, coming in, coming in. Okay, so at any finite t, there is a maximum place where the dust extends to. After that, as Schumann pointed out, the solution is going to match on to a Schwarzschild. Okay, so now I'm going to ask you to do the following exercise. Match the solution to Schwarzschild. Okay? So you know that the solution outside has to be in the Schwarzschild form, but it needn't be in the Schwarzschild form in the same coordinates. Okay? So you're going to have to do some sort of coordinate change and then match the solution to Schwarzschild. Is this clear? Okay? And this is the first exercise. Exercise number 2 is compute the radial null geodesics in this joint.
Actually, we should take a f is equal to f naught, and then at f is equal to f naught, we should
You should match with Schwarzschild and move to a coordinate system in which the metric is continuous across this thing. Continuous, first derivative continuous. Obeying everything that it should do. Okay? You want to be, that in some coordinate system, in particular find the mass of, by this matching, find the mass of the Schwarzschild. And what, this is a matches with Schwarzschild radius, but with Schwarzschild geometry, with which mass? Okay? So what I'd like is a metric in one coordinate system, which is manifestly Schwarzschild outside, or manifestly coordinate equivalent to Schwarzschild, or you've shown this coordinate equivalent to Schwarzschild outside, and is the solution inside. So either you may perform coordinate changes of this solution. You see, this tau will not be Schwarzschild type. Okay, so the solution will be properly Schwarzschild coordinates only after a coordinate transformation. Otherwise, it will be very, very discontinuous at this point. You will not at all be able to see that the solution is continuous. Okay? So, match the solution to Schwarzschild, compute radial null GOD6 in the solution. Now, every time you hear compute GOD6 in some geometry, you think, okay, it's a complicated task. But radial null GOD6 is a very easy task. Why? Because it's just putting the condition ds square is equal to 0. That fixes it. Okay? So, compute the radial null GOD6 in this task, in this geometry. Okay? And this is now the next point is the key point. Find the event horizon of this geometry. So the event horizon what is the nature of the event horizon? The event horizon is a codimension one manifold. Okay. So clearly it is the surface f is equal to f of tau, for instance. Okay. Or you might prefer to express it as capital R is equal R, the lil r is equal to lil r of tau. Some surface in the space-time, that is the event horizon. Now the important point is, okay, this metric clearly has a singularity. The singularity is that tau is equal to tau naught. Also at f equals 0. But let's see, okay, good question. Is f is equal to 0 singular when tau is not tau naught? Yeah, okay, so that's a good question. Is f equals 0 singular when tau is not tau naught? No, then it is not. Let me explain. Let me explain that. Okay. When tau is not tau naught, let's look at this. Let's look at this geometry. In order to check whether it's singular or not, what I want to do is to check whether it's the origin of polar coordinates in R3. Okay, so this is df squared, it's 4 by 3. Well, let's check. This is df squared by 9 into f to the power 4 by 3 plus f squared by f to the power 4 by 3 d omega 2 squared. Now, what I want to do is to turn this into d alpha squared. Okay? So clearly the kind of coordinate change I want to make is df divided by f to the power 2/3 is d alpha. Okay? Have I missed a 4 somewhere? Okay, I'm going to work it out and then we may have to trace back for numbers. You see, so df divided by f to the power 2, no, actually it's good, is equal to df to the power 1 by 3 times times 1 by 3.
No, times 3.
Times 3. Thank you. So 1 by 3 here. Yeah? So let's call f to the power 1 by 3 alpha. Then this thing here is d alpha squared plus alpha squared d omega 2 squared, and therefore is perfectly smooth.
So
This explains that 1 by 9.
1 by.
Yeah, so the 1 by 9.
I was feeling very queasy of that.
Okay, the 1 by 9 had to have been there. So you see, this geometry looks funny at f equals 0, but it's actually smooth at f equals 0 at any tau not equal to tau naught. This is the point. We didn't start with a black hole. We started with a cloud of dust in nice smooth space. It wasn't a singular space. However, we create a singularity at tau is equal to tau naught. Now the question that I want the answer to is, can this singularity be seen by an observer sitting outside? So this solution, as you will see when you do these exercises, matches onto a black hole, so creates an event horizon. The question is the singularity inside the event horizon, on the event horizon, or outside the event horizon?
It matches with the singularity, the singularity, stripless, and the event horizon, they all converge at the same point, the same limit point.
You're talking about the Schwarzschild solution, okay? But we've got firstly another solution, and secondly we're asking a slightly different question. You see, in the Schwarzschild geometry, what I think what you're talking about is this Penrose diagram, and it's clear from here. Yeah, this matching up here, let's say at any finite point here, I want to know the question, can I see the singularity? And the answer from this Penrose diagram is obviously not. Is this clear? However, here the horizon is being formed. The horizon is being formed, the singularity is being formed.
Oh, I see.
Okay?
And for some time we'll be able to see.
You might be able to. Okay? It could be that something funny happens here. You can see it for a while, it lives for a while, you can see it and then it's shielded.
Yeah, some last surface.
Or some amount of surface, yeah. Suppose that it could be, as you suggested, that there's a singularity forms and then the event horizon touches it. Or it could be that the singularity forms but is shielded by the event horizon. The event horizon forms before the singularity. All three are possible.
I would say that the last possibility has to be enforced with a cosmic censorship conjecture.
Exactly. The last possibility is enforced by the cosmic censorship conjecture, but cosmic censorship is just a conjecture.
Yeah.
In this model you will find the last, in this thing you will find the last thing is correct. However, 20 years ago, more than that, 25 years ago I did a VSRP at the IFR with Pankaj Joshi, and he asked me to look at these dust models and to, in fact exactly this problem, and to play around with these three functions, which are actually two functions, and to see if there were special cases of these functions where you could violate. He'd already found some cases where it looked like you could, and to explore more. And I did this sort of systematically. It's not rocket science, as you can see. Okay, and you can find configurations in these models which give you naked singularities. So within this model, cosmic censorship is not true. Okay? Now this model can be criticized on many grounds. Dust is an unreasonable equation of state. Pankaj, since, as many of you know, has been working on this for the last, such problems for the last 25 years, and has, with increasing sophistication, looked at this problem. He's moved away from dust, he's looked at pressure, fluids with pressure, all kinds of things, and he continues to find in many of these models the same phenomenon, that you can find the initial conditions. Actually, the initial conditions I remember that appear in my VSRP were very special, what you might call finely tuned initial conditions. But he's found more generic kinds of initial conditions. He and his collaborators and various other people have found more generic kinds of initial conditions and so on. But one can always question the models within which you work. See, because in the models in which they work and some other people work, what you have in the end is a fluid interacting with gravity. And there's an issue with that. The issue is that the fluid description of matter works when you're at distances large compared to the mean free path. Now, suppose you have fluid coupled to general relativity. You solve those equations and you find that there's a singularity. What can you reliably say about that? You can reliably say that something interesting happens at length scales of order the mean free path of the fluid. Okay? At lower distances, though, there's some more fundamental description that takes over. That more fundamental description could desingularize your. Now, of course, this is a cascade. You can keep saying this. At some scale, quantum gravity takes over and will presumably desingularize everything. But that is the really interesting question in this case. Can you form a singularity that is smoothened out only by quantum effects, not by some other simple classical physics effects? Okay? Can you, by starting from reasonable initial conditions, form a singularity that you form singularities is obvious, but that is naked, that is visible from the outside, that is smoothened out only by quantum effects? If you can, that is very exciting. Actually, the early general relativists very much wanted it not to be true, because for them it meant that general relativity was an incomplete theory. Of course, all theories are incomplete theories. Okay. However, if you can find situations, smooth, nice initial conditions with which you can form form singularities that you can probe in an experiment, that means you've found a way to build a laboratory for quantum gravity. You see, because the current way of trying to probe quantum gravity effects, take particle accelerators, bang them together with energies large enough to become Planckian and then probe quantum gravity, it's proving very tough to accelerate elementary particles. But perhaps there is an accelerator, perhaps the laws of nature can be used to make an accelerator. Set up the right collapse situation and just watch it. If that can be made to form a singularity, near a singularity, quantum gravity effects are surely important. So then we've got a lab which humans would have to get very sophisticated. We'd have to clear out a part of the solar system, do all of that. But that is called conceivable, right? Okay, not us 10 generations down the line. Okay. However, that seems much more conceivable than building a Planck scale accelerator. So that would be very exciting. And the jury is still out on this one. Let me just tell you what is known. Suppose, okay, so firstly, what would one take as, I complain that many people have found, in particular Pankaj and collaborators have found many very interesting situations in which fluid collapse gives you these naked singularities, quite generically. Okay? But my complaint about this is that, why that's very interesting, I think. It is possible that all that will do is give you singularities on scale, mean free path of the fluid, which will be smoothened out by other stuff. So what you want to do is study a more fundamental equation. Kind of equation you want to study is gravity coupled to a minimally coupled scalar, or even better, gravity coupled to nothing. Gravity coupled to gravitons. what more fundamental equation is there than r mu nu equals 0? That's a great equation. Okay? If you can find generic initial conditions in that equation, that will give you naked singularity. Then you're totally sure that cosmic censorship is false and quantum gravity laboratories are a genuine prospect for the future. Okay? I'll tell you the situation as now. In studying the spherically symmetric collapse of, unfortunately you can't do gravitons because there's no spherically symmetric gravitons. But that's why people retreat to looking at minimally coupled scalars. In studying the spherically symmetric collapse of minimally coupled scalars, this is an industry started by a guy called Choptwick. Some 30 years ago. And the following thing. Suppose I take a little pulse of a scalar and I send it in, like we sent in our cloud of dust. Okay, sorry, before I get into all this, is your assignment clear? Yeah. Okay, I think we'll soon stop this class. I'll just tell you some generalities because it's very important. And because it concerns a problem that is, to which the answer is not yet quite known. It's a very important question. Okay, so what Choptwick did was this. He looked at a pulse of a minimally coupled scalar, sent it in, looked at Einstein's equations coupled to the minimally coupled scalar, sent it in, and evolved the equations not analytically because that's too tough, but on a computer. Now, before we start getting a computer, you should have some rough idea about what you should expect. So let's parameterize this pulse of the minimally coupled scalar by, of course it's got a lot of parameters, but there are two important ones. The first one is its mass, m. The second one is some measure of its thickness. Now, m is an interesting parameter, but it's more interesting to convert m into r0, the Schwarzschild radius of a black hole of the same mass. Okay? So there are two interesting length scales in this data. If I put all of the mass of that minimally coupled scalar into a Schwarzschild black hole, its radius would be r0. Let's call it. And then the thickness of that shell. Okay? Now there are two interesting limits. The first interesting limit is r much larger than r0, delta r. And the second interesting limit is r much less than delta r. Does anyone have any guesses as to what should happen in these two limits?
This r means radius of the shell.
Which one? The r0?
This one.
Sorry. Let's take
The first case would, some thin shell dropping into Schwarzschild radius.
very good. In the first case, the shell is so thin that as it comes in, it doesn't touch itself well before it goes within its Schwarzschild radius. What that means is that it's matter that creates a solution that goes within its own event horizon well before it can do anything interesting. Interactions can do anything interesting to stop this happening. Okay? And this intuition can be made precise. In this limit, the solution is essentially the Verdier solution. For those of you know what that is. Maybe we'll study that in the next class. But in this limit, the Schwarzschild solution works. And you can show analytically that this happens. Okay, it's a simple exercise to show this. On the other hand, in this limit,
It's something like a naked singularity.
no, it's less exciting. In this limit, what you've got is a very undense pulse of shell. Now, in this limit, that shell is much more like, it's like a cloud of gas.
Yeah.
Nothing happens. You know, it's like this thing behaves like it's in flat space. It just goes through. You know, it does what it will come whoop and go back out. Okay? In this limit, the energy is spread over so much distance then gravity is essentially negligible. Okay? So that's interesting. As we change this delta r, let's say, let's say this delta r, we start with this in this region. What we have is essentially free behavior of a minimally coupled scalar. Then as we make delta r smaller and smaller and smaller and smaller, nonlinear effects start becoming important. And when we make it very small, the end final solution has an event horizon. So there's a phase transition in the physics, measured by whether at late times there's an event horizon or not. Okay? Therefore, at some critical value of delta r, something interesting is done. And what Chopwick found, and by now is very well studied numerically, what Chopwick found is that at that critical value of delta r, a black hole is formed, but of size 0. Now, a black hole of size 0 is essentially a naked singularity. Okay? So he sees that a naked singularity is formed, but at one critical value of delta r. As we make delta r a little smaller, the size of the radius of the eventual black hole grows like an interesting power of the deviation of delta r from the critical value, 2/3 or something like that. So there's some interesting critical exponent. Okay? But there is a naked singularity at exactly 1. If delta r is bigger, there's no black hole. Delta r is smaller, there's a black hole formed, but without a naked singularity in the process. Okay. At exactly 1 value of r, the space-time goes singular in a nakedly visible way. Okay? So we know that with a fundamental type equation this is possible. However, this is not satisfactory because it happens with a 1-parameter tuning of initial conditions. More generally, if you take a class of initial conditions, you do a 1-parameter set tuning, somewhere, you vary 1 parameter, somewhere you will hit this naked singularity. Okay. This is not satisfactory because you wouldn't be able to use it to build your lab. Because if it happens exactly at one point, you never get back to effect.
We need some.
You need a surface of initial conditions. Okay? Does this happen? Now, but Chopwick worked with spherical symmetry. Can one engineer more general initial conditions so that in some region there is a region that forms this naked singularity? Nobody really knows. It's quite difficult to do. Gravity seems to protect itself, protect its singularities. Okay? In a quite, it's a tough fight to expose. And however, there isn't a theorem which says that cannot be done. There isn't a convincing example, in my opinion, using just good equations. And it's a question of very great importance. Okay. Now, depending on what, let's leave it at that. Let's leave it at that. Actually, in 5-dimensional gravity, compactified in a circle, there is an example of a situation with generic initial conditions that form naked singularities. But we're not in 5 dimensions, we're not compactified in a circle as far as we know. So it's clear. Yes, that's the setup. The setup is about instability of black strings. Perhaps not in this class. Anyone is interested after the class, I can tell them. But that also makes clear that there isn't some very deep general principle involved. It's clear that it's not for some very deep general reason you can never form these naked singularities, because in some very clear situations you do. That's a very interesting question. It's open, and I think the person who proves a theorem about this, or finds a good useful counterexample, will have done some very, very good work. Okay. So, right. So once you do this exercise, I think that's all I wanted to say about gravitational collapse. I just wanted to end with one, with the point of this. What I've tried to explain is that gravitational collapse happens quite easily. These dust models, it happens very easily. Dust is a bit misleading because the thing that stops gravitational collapse, namely pressure, is absent in dust. So it's tuned to happen very easily. But as we saw in yesterday's class, it also happens in some situations, some important physically relevant situations, in places with a lot of pressure, the kind of pressure that exists in the element. Okay? So this gravitational collapse happens quite easily. The details of the collapse process, though, are not yet completely understood. And in particular, the question of whether collapse always proceeds generically without naked singularities or not is a very important and really out there question about which there is a conjecture, namely a cosmic temperature. Okay. Right. So please solve this exercise. But take the right lesson from this solution. The solution is just is interesting because it's solvable. What it really shows is an example of this collapse happening, but you shouldn't think that all collapse situations are this. That's far from obvious. Okay. Any questions or comments, or we'll stop for today. In the next class, I think we'll talk about the curve, the rotating solution, rotating lattice.